Um, okay, so I think that we can start. We have 8 attendees, so welcome all of you to our regular National Edge AI Hub webinar series. Today, Dr. Blesson Varghese from University of St. Andrews will explore how ML models can be trained directly on the devices where they are deployed, unlocking new possibilities for efficiency, privacy, and responsiveness. Blesson, the screen is yours.
Well, thank you very much, Tomas, and a pleasure to be here and to share some of our findings on how you can go about doing on-device learning. I am a professor in computer science at the University of St. Andrews, and I've been looking at this area for the last 5 to 6 years with my team of PhD students and postdocs. So my intention today will be to go through a range of different ideas that have emerged from our lab and signpost you to some of those opportunities rather than get into the very specific nitty-gritty details. Although I will be showing some graphs and some results because I am an academic and I enjoy doing that. So once again, thank you for joining this webinar. So first of all, let me just introduce you to where we are in the UK. So we are located in the east coast of Scotland. So you're likely to have heard of cities like Glasgow and Edinburgh. We are about 1 hour, 15 minutes northeast of Edinburgh and a similar-ish sort of a distance from Glasgow as well. We are known as the home of golf. So if you are a golf enthusiast, you have plenty to explore here. It's historically famous as a place for its contributions to the Reformation. The picture there on the right-hand side is the ruins of the cathedral from the time of the Reformation, and we are home of the third oldest university in the English-speaking world. So we are more than 600 years old now. So it's a place that everybody is very welcome to come and visit. And if you're interested in on-device learning, you know whom to get in touch with. So what am I going to cover today? So I'll primarily be looking at giving an introduction to systems. What are the type of systems that we are talking about? So I'll talk about where we were, where we are today, and where we are headed. I'll be talking about machine learning in the context of distributed systems, some of the challenges in engineering these machine learning systems. And then based on those challenges, I'll be exploring some of the techniques that have emerged from our lab and highlight a few experimental results, and then I'll make some concluding remarks. So thank you very much for your patience as I go through these slides. So let's look at how systems in general work these days. So you've got a whole range of devices, including sensors and actuators. This might take the form of your smartphone or smart glasses, or there might be external to users such as CCTV cameras or drones or autonomous robots in manufacturing plants or even an autonomous vehicle. And typically the expectation is that they would interact with a cloud service provider, whether it's public or private, and you would send a request, get it serviced, and obtain the request serviced back to the device. Now, this generally works well in the internet ecosystem, but you have some issues that you need to be concerned about. There's the issue of privacy because data often has to leave the device. There's the issue of responsiveness because of which many applications still haven't emerged in the real world. And then, of course, there are issues around bandwidth because you're going past a wireless hop, which means that you are bound by the bandwidth of the wired network that will be there behind the first hop. So these are some of the challenges that you will find in existing internet scale systems. Now, that is not to say that the internet-based systems don't work, they do, but we are looking for something perhaps that will help us leapfrog into the future. I'm just going to show this image that I usually show in many of my talks. One of a smartphone and one of a toothbrush, a very basic thing that most human beings use, perhaps perhaps a couple of times a day. Now that's not to suggest anything about oral hygiene, but we have more than 6 billion smartphones in circulation and less than 5 billion of these manual old school toothbrushes in circulation. Now here is another picture, again a smartphone and the Apollo lander. Surprisingly, your smartphone has more compute memory and uh, power capabilities than your Apollo guidance computer that helped the Apollo land on the moon. So your smartphone is usually between 4 to 16 gigabytes of RAM, and that's an average spec in the market. You have 32 to 128 gigabytes of storage and extendable, and some are even GPU enabled or some sort of accelerator enabled. But your Apollo guidance computer was fairly modest with 4 kilobytes of RAM and 32 kilobytes of storage. So pretty much everybody has got a device in their hand that could help them land a space shuttle on the moon. Even if you think about wimpy, what we might consider as wimpy devices, which is like a USB charger, the microprocessor on it may have more compute and storage than what was there on the Apollo guidance computer. So this is where the systems that we are seeing now are trying to move towards. So you have the extreme edge, again, the same devices that I was mentioning before. You have the cloud, but now there is another layer over there where people are starting to think about doing compute. Now, this is not a layer that has been superficially introduced. It's always been there. It's just that we have not taken note of it for general purpose compute. So you might think of a home router or a wireless access point or an internet gateway. They have always existed in the internet ecosystem, but we have never thought about doing general purpose compute on them. Or it could be luggable data centers or on-premise data centers that might sit on the top of buildings, or it might be a mobile base station to which you have a micro data center that's connected. So these are all resources that have existed, but the question is, can we do general purpose compute on that? The advantage of doing it is you have some privacy preservation because your data is not really leaving your legal jurisdiction. It's probably still within your country, within your district, within your county. It improves responsiveness to an extent because um, the amount of time that is required to process data is directly proportional to the distance that data has to travel. So if you're just processing data one hop away from the extreme edge, then you're improving the responsiveness. And of course, you're reducing the ingress bandwidth demand because you're pretty much, if you're dealing with the edge and the device, you are pretty much dealing with a wireless connection rather than a wired connection. So the ingress bandwidth into the core of the network is significantly lower when you start using the edge for pre-processing. We think this might be the way systems are headed for the future. Uh, this sort of compute, what is called as edge computing, making use of that edge layer either on resources that already exist or by introducing new resources onto that edge of the network, is what we are referring to as edge compute. It's already here. The press cuttings that I have there are pretty much all from the early 2020s, and as we now move into the second half of this decade, there are lots of other opportunities that have emerged in this space. So what happens now when you have ML in the space of systems? So that's what I want to briefly discuss and lay the groundwork for the type of challenges that I'll be shortly introducing that are there when you have ML in systems. So think of your devices that are generating data. So I've just shown that as an image, but it could be a stream of images, perhaps because of video or any other form of data, any other modality of data. So typically, the reason why you need machine learning is so that you can interpret the data that's generated by the sensors. You want to make some sense of the environment. So a classic system might just have a machine learning model, such as a deep neural network somewhere in the cloud, and you send all the data, you get it processed via the neural network, let's say, and then you get some response back on the device. Now, this inherits the same problems as I showed you as the systems of yesterday. This two-tier model, not necessarily privacy preserving because your data has to leave the device. It's quite bandwidth intensive and it's not responsive for real-time applications. Now, on a smartphone, it might work, but on your smart glasses, it might be a bit more of a challenge, especially if they're sleek glasses, and much more of a challenge if it's a critical application like um, a, a car, for example. So it's not responsive for real-time use. So then people started saying, let's re-engineer the system, let's do something slightly different. So people started putting the machine learning model on the device itself. They started doing local training, only sending the models onto the cloud, and then using a model on the cloud to aggregate the models that every device sent, and then send a global model or an updated model back to all devices, and they could continue learning. And of course, the learning between the devices are shared. Now, this is the notion of what we call as federated learning. So this has been in the literature for quite some time, probably since 2017, 2018 sort of time frame. Now, the key points here is it is privacy preserving to an extent because your exchange is not of the local data, but it's of the local models. So you still have a further step to go from models to the original data, which is a bit more difficult than just interpreting the original data. It's less bandwidth intensive because your models tend to be typically smaller than um, the input stream, especially if it's at high definition or whatever. And this, but the key challenge here is that it's not responsive for real time. It all depends on how fast your local device can do the local training, and that's generally not possible in a quick manner because you're still working with your smartphone and your smart glasses, which don't have substantial compute or memory. So one of the challenges that we think are there in these sort of distributed systems where you want to do on-device learning, but you really can't, is that ML systems cannot efficiently run on small devices. Now, this is a well-known problem. Many people have attacked it from many different angles. So let me just tell you why or tease apart this challenge a bit more. So if you think about a small single board computer, a small form factor device, its memory might be from a few megabytes to a few gigabytes. And of course, compute is not going to be substantial either. And the classic ML algorithms or models were not designed for these sort of environments. So take an example of a Raspberry Pi 3, which is, of course, a previous version of a Raspberry Pi. But if you use it to train one round of MobileNet, which is a deep neural network that is actually designed for mobile phones, and if you try to do it in the context of federated learning, you would require 8 hours of training for one round. Now, typically, you would require 60 to 100 such rounds on a medium-sized data set. So you can imagine it's simply not practical. ML systems are simply computationally inefficient to run on resource-constrained environments. And these sort of single-board computers are an example. Now, of course, it's going to be much more challenging if you're going to um, microcontrollers or anything at that scale. But this is a well-known challenge. So we'll be talking about how we have attempted to address some of the issues around this challenge. So hence, it's also an opportunity for us in the on-device learning space. The second problem that we have encountered as we have tried to study ML systems is that they are inherently sequential, and I'll explain what that is in a moment. So think of your devices, which are doing some local training, and think of the cloud system, which is doing some sort of global aggregation. So typically, the way the system would work is you get your inputs, you then train, and then you generate those models, you send them to the cloud. On the cloud, you aggregate. But of course, as you can see, it is inherently sequential in nature. When the device is computing, that's the step number 2 that I've shown there, the server is not computing anything. It is idle, which is step number 4, because it hasn't received any data from the devices. And it generally tends to be a synchronous system if you want high accuracy for these type of systems. And when the device is communicating, that's step number 3 to the server, the device is idle, which is step number 2. And when the server is computing, which is step number 4, and communicates to the device is actually idle, which is step number 2. So you can see there are lots of idle times that are there in these type of systems because they are inherently sequential in nature. Now, what that means is that a lot of the devices that operate in a distributed machine learning system may have low resource utilization, which means that you have created an inefficient ML system. So we'll be looking at ways in which we might be able to mitigate this challenge. And so it is an opportunity for us as well from a research space, from an innovation space, and so on. One of the third problems that I will be talking about is how ML systems are inherently memory intensive. And I will tease that for you in a moment. So if you think about edge resources that have GPUs, they typically tend to have limited memory compared to cloud data center style GPUs. The basic algorithm that is used to run any machine learning algorithm is the one created by Professor Geoffrey Hinton, the Nobel Prize winner for physics. And that algorithm is called backpropagation. So that is the basic mechanism by which any ML model gets trained or it learns. So you have an input, and then you have the neural network layers. There's some training going on. It creates the activation in the forward pass that gets moved on to the layer two, again forward pass in layer two, and it then comes to layer three, computes a global loss, and then you start the back propagation or the backward pass, in which the gradients then get sent back to the layers where the weights of the layers get tweaked. Now, this is the classic method, but because it's got this forward and backward dependency, it is actually memory intensive. Or in other words, because the gradient of a layer depends on the output of the previous layer, all those gradients need to still be there in memory. And all activations also need to be retained in the GPU memory during the forward pass, because of which backpropagation is memory intensive. It works beautifully as an algorithm. It gets you the accuracy that you might be expecting, but it is memory intensive. Now I want to show you another figure here. The one on the top is the GPU memory versus batch size. So if you have a small batch size, you can do compute with a very limited GPU memory. But the problem is the time taken for training is going to be significantly high. If you increase the batch size, your GPU memory is going to increase substantially, but you might get it to do faster. But the problem is here is that there is this trade-off between memory and batch size. So reducing the batch size will reduce the memory use, but reducing the batch size increases the trading time. So what we have observed is that production quality ML models simply will not fit on modern edge GPUs. So we need mechanisms to circumvent this problem. So I will be talking about this. So this lays the groundwork now for me to talk about some of the techniques that we have come up with. So let me just give you a primer on how do you build ML systems? What sort of methods might you have? So you have multiple options. You can do on-device learning. You can build something from scratch. So if you think about a new build house, you're building it from scratch rather than occupying an old house. And that is a legitimate way to build ML systems. You can change the way in which ML models work. Are there interesting alternatives to backpropagation to build models? And we will be exploring that very briefly. Then I mentioned something about idle time and the low resource utilization. So the question is, can we optimize the training pipeline, and can we maybe make use of parallelism? And I'll very briefly talk about that as well. And then, of course, you have the possibilities of making the machine learning models themselves small so that you have limited compute or limited compute expense on the device. And that's the process of miniaturization or squeezing them. And typically it's called compression, and there are a whole range of techniques, and I'll very briefly mention that as well at some point in my talk. And then we have this method called offloading, which is partitioning a neural network and splitting it across the extreme edge and an edge server. Now, the good thing about that method is that it'll preserve privacy and accuracy, and we'll talk about that as well. So we'll start from the bottom because I'll start talking about offloading. Then we'll go on to a little bit of parallelism. Then we'll talk about on-device learning, and then we will conclude by talking about compression. And I hope I will be able to conclude this in the next 10, 15 minutes or so. So let's look at how offloading-based systems work and what do we mean by that. So if you look at the right-hand side of that figure, I've shown three tiers, which is the cloud, the edge, and the devices. If you think about native DNN execution or the way in which DNNs would have typically been run in the past, you would see that they would either run on the device, the edge, or the cloud. But with offloading, we have the possibility of partitioning a neural network and putting certain layers on each resource tier. So you have many different options depending on the environment, depending on the compute capabilities, depending on the use case, you have the possibility of partitioning and putting this across the device and the edge, or the device and the cloud, or the edge and the cloud, or across the device, edge, and cloud. Of course, you have to take into account all the performance metrics that you need to be meeting. We demonstrated this work. I think we were one of the first teams to demonstrate that you could actually do distributed DNN execution in certain environments and actually achieve near native DNN execution performance. So how does offloading work in the context of federated learning? So if we were to bring that notion of offloading into federated learning, how might we help federated learning? So the first technique is, of course, partitioning the model and offloading some of the compute onto an edge server. What that does is it alleviates the computational burden on devices. And at the same time, it also mitigates the problem of stragglers. So in this example, if you think about the glass, the smart glass that's there, it is likely to be slower than, let's say, a high-end smartphone. And if you wanted to complete training the same time the smartphone may have completed, you probably want to put fewer layers on the smart glass. And this notion is called as DNN partitioning based FL. The work that we have developed out of this is called FedAdapt. So let's see how it works. So you have a collection of neural networks and neural network for each device, and you partition the model at different layers so that you can offload one part to the edge and one part, place one on the device. So in effect, you are alleviating some of the computational burden on the device. Now, this works well if you know the configuration of every device and if you're monitoring it aggressively at the end of every round. Can we bring in some automation? Perhaps we can use reinforcement learning so that you can adapt to, let's say, the changing network bandwidth. So you monitor your environment and you generate a new plan. So let's look at some relatively small models that we have used in this context in a setup where you've got a collection of Raspberry Pis and a Jetson Nano. So if you didn't have the sort of mechanisms that we were talking about, the partitioning-based federated learning, you would typically, for one round of training, be spending somewhere about 1700 seconds in this case. But then with federated learning, sorry, with FedAdapt, the techniques that I've introduced, you get about close to 2.5 times speed up. The accuracy is the same as the original federated learning accuracy. And you can find more about this piece of work in our paper entitled FedAdapt. But as you can see, that's not good enough. It's still not coming down to the scale of seconds or sub-second sort of scale. I'm not going to talk about what we have done to get it down, but we have optimized the communication that is there in the system. And what we were able to show in a second piece of work called EcoFed, which is all about optimizing the communication in a system like FedAdapt, we were able to bring down those times to, let's say, 8 seconds, as you might see in the light green bars that are there, 8 seconds or 22 seconds. Now, bear in mind that these are slightly larger models than the ones that I showed before, but we have been able to bring down the training time. But again, we still need to go further down, probably to the sub-second sort of range to perhaps, be able to do this in some sort of real-time setting. Now, you can read all about this work in this publication called EcoFed in the IEEE Transactions on Parallel and Distributed Systems. Now that's just signposting you to some techniques that we have created, both at the compute front and the communication front, and how we try to address some of those challenges around, running machine learning on small devices. So That's where FedAdapt and EcoFed were focusing on primarily the compute and the communication. We started looking at the system again, and we started saying, how do we now reduce the idle times that I was telling you about earlier? How do we break the sequential dependencies that are there in ML systems? And so we started studying the anatomy of the training pipeline. So if you think about the FL system again, where you compute on the server, you send data to the server, then you compute on the server, and then send data to the device. If you think about that model, how does it work? So you have computation on the device, then you send data to the server, then you do some compute on the server, which is primarily the local aggregation, and then the server sends data back to the devices, and then the device will continue to do compute. And as you can see, there is a fair amount of idle time that's created. So we said, why don't we change the fundamental way in which um, ML works? Why don't we change this sequential dependency? So we came up with a piece of work called Piper, where we started splitting the computation on the device into mini batches, and we started packing this pipeline. And when you pack this pipeline, you end up with less idle time. Now, of course, we are only showing one round here, but if you had multiple rounds, you would only have an idle time at the beginning of training and at the end of training, but the rest of the pipeline would be incredibly well packed. So we get rid of some of the idle time. Now, although I am merely showing this to you as a figure, an abstract figure, trying to demonstrate that we have gotten rid of the idle time, it is a significant engineering challenge, and it involves a lot of reworking of the ML algorithms to make this to work. This piece of work is called Piper, and as you can see, federated learning. Uh, if you compare Piper to federated learning, we are able to get substantial speedups. So bigger the model, the better the speedups that we obtain. So the second figure is of ResNet 18, and you can see we go from more than 3,000 seconds per round down to the order of a few hundred. So this is a technique that you could possibly integrate with some of the first techniques that I showed and um, reap the benefit of both pipeline parallelism and some of those initial techniques that I mentioned. Again, you can read more about this in the publication called Piper in the Journal of Parallel and Distributed Computing. There have been substantial work since then that we have carried out in this space. So we have looked at how you can reduce the idle time on heterogeneous devices. That means that when your device configurations are all different. So it's a smartphone, a smart glass, and maybe a Fitbit that's working together. How do you reduce the idle time in that sort of a setup? And that's the piece of work there called Fed Optima, and you can read up about it. There is an archive link for it. We have made it public, and you should be able to access it. Similarly, there is a piece of work that we have done when you want to reduce the communication and computation simultaneously while also improving the accuracy in the setting of heterogeneous devices. Now, that's a much more difficult problem, and we have had to rewire FL quite significantly. And that piece of work is called Ampere. And that is an interesting piece of work as well that you might be interested in to see how you might be able to tackle some of these multiple objectives at the same time. Okay, I'm moving forward to the third out of the four pieces of work that I wanted to signpost in this talk. So the third one is around memory efficiency on device in on-device learning. And here I'll be talking about backpropagation and how we have come up with a different technique altogether to circumvent the drawbacks of backpropagation. So the way we started this study was to look at what are the alternate training paradigms that exist to backpropagation. Now, we know that backpropagation works well, and so it's been adopted. But we were trying to study this along the axis of accuracy and GPU memory. So if you think about low accuracy, high accuracy, low GPU memory, and high GPU memory, where do the alternate training paradigms that exist stay? Where are they situated or positioned in relation to this axis that I'm showing here? So backpropagation, high GPU memory, but as I said, you get very high accuracy. Then we looked at local learning. It's another competing method, and I'll talk about that briefly. Again, similar to backpropagation, high GPU memory and high accuracy. There are a few other methods that are out there that have come up over the last decade or so. One is called feedback alignment, and the other one is called signal propagation. So they are alternate training paradigms. Um, so if one of these were to be adopted, you would be doing machine learning in a completely different way to backpropagation, for example. Now, the ideal zone that we want to be in is what I called as a Goldilocks zone. So the Goldilocks zone is where you have optimum GPU memory. So low is what we would consider optimum and very high accuracy. So the question is there any method in that space? And the answer is no, there aren't any methods in that space. So we started thinking about, can we do anything with existing methods and bring them into the Goldilocks zone? Can we try something different on any of these methods and bring them into the Goldilocks zone? And when we did this exploration, we identified that local learning is the method that has the most promising potential to be brought into the Goldilocks zone. So we started experimenting with that. So how does local learning work? It works very different from backpropagation. So in backpropagation, as I said, you have the forward pass and the backward pass, and every layer is dependent on the output of the other layer. But in local learning, that's not the case. So L1, L2, and L3, you only have forward passes through them, but you've got an auxiliary network that's connected to them that creates a local loss. And you could effectively treat a layer and its auxiliary network as one unit. So if you treat that as one layer, you only have a forward pass. You do not have a backward pass. So you get rid of the backward dependency. And then the question is, because you're only dealing with one layer, can you do anything clever to make it fit in memory of the GPU device? And that's effectively what we have been doing with local learning. So the key things to note here is you are not creating a global loss, but you're creating a layer-wise loss. So those layer-wise predictions are possible via an auxiliary network. So each layer is trained independently with its own loss. So the activations only need to be retained for a local region. You're not retaining it for L1, L2, and L3. If you're doing compute related to L1, you only need to retain it for L1. Now, classic local learning will use very large auxiliary networks, which will result in very large activations. So that was a major challenge that we had to deal with. So we need comparable GPU memory to backpropagation. And that is what we were aiming for. So we came up with a system called NeuroFlux, which I'm not going to talk about, but the two main contributions was about adaptive auxiliary sizes and adaptive batch sizes. So how did we make it work? So these are the two key techniques. So one is adaptive auxiliary networks. So we came up with a mechanism to design new auxiliary networks in the local learning paradigm, which reduces the activation size so that the memory required is much lower than backpropagation. So if you look at classic local learning, which is the line with the triangles on it, you will see that it requires much higher GPU memory than backpropagation. So on a GPU memory front, it's a major challenge. And then if you look at the lower bound of what might be possible, if you look at inference, which is the gray dashed lines that you see at the bottom, that's probably as low as you might be able to go. And you can see that backpropagation sits just below classic local learning. And our method of adaptive auxiliary network, which is a green line, is where you have this notion of these new auxiliary networks that where your memory is brought as low as possible, as close as possible to inference. What that what that means is that it gives us the possibility now to train a machine learning model on an edge GPU with the same amount of memory that you would have used for inference. So which means that you can effectively use an edge device, a GPU edge device, for both training and inference, because your training budget is not any higher than your inference budget. So that's one of the key observations or takeaways from that. The other notion that we came up with was adaptive batch sizes. So typically in the machine learning world, every layer is trained with the same batch size. And we said, okay, let's flip that on its head and let's see if we can train different layers with different batch sizes. And the rationale for it, so if you look at this particular model, which is a 16 layer model, so I believe it's a VGG 15. If you look at the orange bars, which is the amount of GPU memory that's used by each layer, it's the initial layers that use substantial GPU memory. So if you allocated 600 and whatever this number is, 630 megabytes of GPU memory for training this entire model, what will end up happening is as you progress in your training, there will be a lot of unused memory. So we said, can we make use of this gray bars or this unused available memory for training other layers or increasing the batch size? So we train more for that particular layer. And so it's a combination of these two techniques that actually helps us. And it's a piece of work called NeuroFlux. So let's look at some very basic results. So let's take an example. So I'm just going to refer to, so we're showing the results here for three models, VGG 16, VGG 19, and ResNet. And we're showing it on Tiny ImageNet, which is a relatively larger data set than CIFAR 100 and CIFAR 10. So let's take the example of VGG 19 on Tiny ImageNet. So that's the bottom row and the second column. So if you look at classic local learning, you will see that the lowest budget that you will be able to train the model is at about 300 megabytes. But if you do that, you are spending about 20 hours of training time doing it. Backpropagation on the same 300 megabyte budget, you will probably do it in 15 hours. But for that budget on NeuroFlux, the new methods that I just described, you will do it under 3 hours or 2 hours. And you will also appreciate that with NeuroFlux, you can do it on much lower memory budgets than what was previously possible with backpropagation or classic learning. And that seems to be a relatively generalizable result across all the models that we tested with. You can find this publication in the conference EuroSys, and that's available publicly as well. So we have done some more work past this. So we have looked at convolutional neural networks and how we might, use alternate methods to backpropagation, but we've also done this in transformer-based models, and we have seen similar success. Now let's talk about the final piece of work on compression and the techniques around this. So by compression, what we mean is we want to take a pre-trained model, which is maybe relatively large because it was not designed or created for a small device. And we want to run some techniques on that pre-trained model and create a small model so that you can deploy it on a small device. So here the focus is not so much learning, but it's inference. So I've discussed many techniques here about ways to run the entire model on the device. But in this particular case, we are thinking about deployment, and we are looking at what compression means. So compression means taking a dense neural network and then creating a smaller compressed method. So the idea here is to reduce the number of parameters that are there in a neural network. There are so many techniques out there: neural architecture search, quantization, distillation, and pruning. And our work is primarily focused around the area of pruning. There are two types of pruning methods. So one is called unstructured pruning. So unstructured pruning simply means that within your network, the values within a layer are set to 0. So it's setting parameters to 0. It's not physically removing them. Then you've got the notion of structured pruning, where you can remove components of a layer fully. For example, the kernels. If they're all set to 0, then there's no reason to have them sitting in memory, even with 0 values. So unstructured pruning, primarily setting parameters to 0. Structured pruning is removing parameters. Now, of course, each of these have their own challenges that they come with, which I'll talk about shortly. So let's examine the post-pruning performance of these methods. So think about the compute and memory efficiency of structured pruning and unstructured pruning, and think about model accuracy as well. Again, low and high is what we are considering. So unstructured pruning, very high model accuracy because you are not playing with the structure of the DNN. Rather, you're just setting certain values to zeros, and it'll have low compute efficiency. Structured pruning, though, it'll have uh, very low model accuracy because you're removing parts of the network, but it has very high computer memory efficiency because you've removed parts that do not now need to be computed. So again, the ideal Goldilocks zone is somewhere different. So the question is there anything that can be done whereby we can get high model accuracy and very high efficiency in terms of compute and memory? Uh, and that's a piece of work called DNN Shifter. And the way we attempted this was to see whether we can combine structured pruning and unstructured pruning. Um, and some of the challenges in pruning that we've considered are how can you rapidly generate a range of DNNs suited for different operational conditions for heterogeneous resources, and how do you spatially compress DNNs while maintaining the accuracy as well? So if you're a 90s kid, you may be familiar with this movie, Honey, I Shrunk the Kids. So the dad invents a shrink ray machine, and he fails multiple times, but then accidentally there is a time when it works, but he ends up shrinking his children. So that's the kind of compression we want, because in shrinking, he didn't destroy his children. In shrinking, the children still worked as human beings, as normal human beings. So we want spatial compression that works while maintaining accuracy. So how did we go about this? So the way we go about this is you start with unstructured pruning, and then you gradually move towards structured pruning. Now, although I am conceptually presenting this as a lot more engineering work that goes with it. Um, so in unstructured pruning, what is done is to identify the parameters that can be set to zero. And as you progress in your unstructured pruning, you start to group these zero values together. Now, that's again based on a hypothesis that's out there by somebody named Jonathan Frankel called lottery ticket hypothesis. And it's based on that lottery ticket hypothesis that this is being done. And you eventually are able to group your zeros together, and then you can apply structured pruning and remove those channels altogether. So that way you reap the benefit of higher accuracy with unstructured pruning without actually destroying the model or its utility by just directly applying structured pruning. So you make sure that the bits that you're removing are only the bits that will not affect the accuracy of the model. So it's a combination of unstructured and structured pruning. So we start off with unstructured pruning, and we come at the other end with structured pruning when we have zeroed channels. I won't be talking about the system, but you can read more about this in the paper. So if you compare the accuracy of the model that is compressed with DNN shifter to some of the other relevant baselines, you will find that DNN shifter does preserve accuracy at very high compression ratios. So if you have a compression ratio of 256, for example, VGG16 on Cypher 10, the first block that I'm showing, you kind of maintain reasonably good accuracy even at higher compression ratios, whereas some of the other methods will have significant drop in accuracy. Now, this is not to say that this method is perfect. As the model gets bigger, the data sets get bigger, you do take a hit. You do take a hit. So um, there are challenges to this method as well, which we have subsequently tried to improve. You can also get speed ups on devices, on CPUs, for example. And you can read more about this paper in the Future Generation Computer Systems Journal. Um, we have tried this on LLMs, and surprisingly, it works well. Now, of course, not the exact same technique, but conceptually the same, where you apply unstructured pruning and structured pruning together. We call it as composite pruning. Again, you can find this in the context of LLMs, where we have pruned pre-trained large models like Llama and whatnot, and we have been able to run them on very small devices with significant speed up without taking much of a quality hit. And you can read more about this as well. The work is called Mosaic. So I'm now planning to conclude my talk because you've been very patient in listening to me for the last little while. I've introduced a number of different works: FedAdapt, EcoFed, PyPy, NeuroFlux, DNN Shift, and Mosaic, and so on. They're all examples of different techniques and systems that are attempting to make ML work on resource-constrained environments. We have around 11 patents that have been filed from these works, but there are still numerous computational and communication bottlenecks. It's still an open space for exploration. And some of the system challenges around heterogeneity, scalability, fault tolerance, all still need to be addressed. What we have done is we've taken the core algorithms and have tried to improve how we might get certain system benefits out of them. But if this has all got to go into production, there are still a whole range of things that we need to consider. So thank you for your attention. Just very briefly, who we are: the Edge Computing Lab at the University of St. Andrews. We tackle systems-oriented challenges at the intersection of edge computing and ML AI. We have a whole range of students, postdoc, and PhDs. We also very proudly contribute to the National Edge AI Hub that is led by the Newcastle University. And we have a whole range of industry partners and organizations that support and fund us. If you're interested in doing a PhD in this sort of an area, do get in touch with me. That's some shameless advertising at the bit. But once again, thank you very much for your attention, and I'm very happy to have a discussion now.
Thank you.